This problem is the one for benzene, and it's simply asking for the speed of light. The problem reads, what is the speed of light in benzene? The equation is really simple. I know the equation, but I still want a page in order to make sure that I write it down just the way it is in the book. So the index of refraction equals the speed of light in vacuum divided by the speed of light in the material. Respectively, we would have V equals C divided by N, and that would be 3.00 times 10 to the 8 meter per second, so 300 million meters per second, or 300,000 kilometers a second, or 186,000 miles per second. Divide by the index of refraction of benzene, divide by 1.501. Pretty much exactly going to be 2.00, right? If I do that, 3 divided by 1.501. Yep, pretty much around at 2.00 times 10 to the 8 meters per second. By the way, when I plug this in here, the index of refraction has no units, so therefore you don't see any. As far as the problem is concerned, I'm already done with it, but of course, as usual, I want to show something extra, and that is that the speed of light is a universal constant. Light always goes at this speed here, even in the material. But, here I pulled this up, Wikipedia article on the index of refraction where it says microscopic explanation. At the micro scale and so on, in electromagnetic wave phase and so on. So if you read through this, the kind of casual explanation is that as light is traveling through a transparent material, of course through a non-transparent material it's simply absorbed by the atoms, but in a transparent material it travels through it at the speed of light, and it's being absorbed and then re-emitted, and then being absorbed and re-emitted. And basically that's what they say here. They say it's more exactly with, as you can see, the electric and magnetic field that make up the electromagnetic wave that is light. And so it goes with the speed of light, takes a pit stop at an atom, goes again with the speed of light, takes another pit stop, speed of light, takes another pit stop, and overall, with all those pit stops in between, the overall velocity of light in that material is less. In the case of benzene, it's only 200,000 kilometers per second. I still have a little bit more, and that's this one here. This would be a typical experiment. This is a hollow semicircular shell made out of transparent plastic, and we would fill water in this one, and then I don't know about the lining of the side here, but what we would do is we would put a light source here, like a little laser, and it shines onto the water. So remember, there's already water in here, and then it's being refracted, and there should be more of an angle of refraction in this one here. I'm not sure what this one is on the right hand side. In any case, so then it's being refracted. Some of it is reflected as well. So that's the way we determine the index of refraction of water. Now, alternatively, in this hollow plastic shell, you can also fill in some other kind of liquid, such as benzene. And I did that once during a test for students. I had everybody just take one measurement. I put it in the back of the room because it really smelled bad, and then everybody took their measurements, figured out what the index of refraction is of benzene. I don't remember, but I'm thinking that they probably came pretty close to the 1.5 or 0.501. And at the end of the lesson, I noticed, since I'm not a chemist, what the benzene did to the plastic shell, and that was it melted it. respectively 8 up on it, and I had quite a benzene mess on the table. Fortunately, it was a good lab table, and obviously I never did that experiment again after I cleaned it up with benzene, that is. We always do it with water, and just with water. And I also have the applet available. This is the bending light applet. In this case I clicked on more tools because you have a speedometer. I don't know how such a speedometer would work for light rays, but here it is in the simulation. I put it in the custom index of refraction for benzene, and then here I turn on the laser and I put the speed of light here, and it measures 1c, and here it measures 1c on the reflected one. Inside it measures 0.67c, and if you look at it, 200,000 kilometers per second versus 300,000 kilometers per second is 2/3, which is 0.67 times the speed of light in benzene. This problem says a light ray and air is incident on a water surface at a 43-degree angle of incidence. Find A, the angle of reflection, and B, the angle of refraction. So we have water with the index of refraction of 1.33 and air with an index of refraction of 1.00. By the way, the exact index of refraction for air is 1.00029, but that's so close to 1 that we usually round it to 1, especially considering the significant figures when we're using actual measurements. Okay, so we have an incident angle of 43 degrees here, according to the law of, I'm trying to make a little circle there. It doesn't allow me to make a little circle for degrees. The pen that I'm using here, boy. So according to the law of reflection, we also get 43 degrees because the law of reflection, I could have typed that, would have been better. We'll do that the next time. So the law of reflection is the angle of incidence equals the angle of reflection, and then of course 43 equals 43. Okay, the next one here I'm going to type. So the law of refraction, which is also called Snell's law, is going to take this one out of the way here. Is the, in this case, index of refraction of air times the sine of the angle as it comes from air equals index of refraction of water times the sine of the angle as it enters the water. Okay, the unknown is this one back here. That's what we're supposed to figure out. So the algebra on that one is going to be that angle equals the ratio of the refractive indices times the sine of the angle on air, and then, so what I did is I divided by the index of refraction over here, and then now I have to take the inverse sine of this whole thing, and I have to put parentheses around all of this here because it's all inside the inverse sine, and then it's pretty much plugging in numbers. And what we're going to come up with is in degrees. So I'm going to first I'm going to check my mode. I'm in degrees. Yep. So I'm going to take the inverse sign, and then it's going to be 1.00 divided by 1.33 times the sine of the 43 degrees, and I come up with 30.8, or around it 31 degrees. I'm not going to write this down, hoping that you will either do it yourself or watch my recording. Using an applet, could be like this here. Click the button, take a protractor, put it exactly there. There we go. And I already got water and air, and then I turn it to 43 degrees, almost there. That looks like 43 degrees. I'm going to look here, and that looks indeed 31 degrees. And of course, this one over here is 43 degrees for the reflected angle. This problem says a ray of light traveling in material A strikes the interface between materials A and B at an angle of incidence of 72 degrees. The angle of refraction is 56 degrees. Find the ratio NA over NB of the refractive indices of the two materials. In this case, I always like to have visuals for these kinds of problems, and I took one from the book and I had to adjust it. That's why you see all these kind of strange things around. You're trying to block out other things, and I guess there's a point A that may mean material A, and then I have material B here. And then of course all I need for this one is Snell's law. And the way I would have to write this is that the index of refraction of material A over the index of refraction over material B. Let's see, that's what, yep, that's what we're supposed to get, is going to be sine of the angle B divided by sine of the angle at A. And of course, you should be able to see the algebra that we get from this, where this one, where the NB is divided down here and the sine theta A is divided over there. And that then comes out with a ratio with no units. It's easy enough to calculate on a calculator. I just gonna use the applet here for now. I'm gonna change both materials to custom because I don't know what they are. I just gonna do something here or something there, and then I'm gonna do 56 degrees. No, it's at 72 degrees is incident, so that's 71, so that may be 72 right there. And then down here I would have to have 56, which is here, so I'm gonna, for example, increase the index of refraction until I get to 56 right there, and then I would do the ratio of 1.11 over 1.27 divided by 1.27, and I come up with a 0.87, and I'm looking at my solution manual, and there it says also 0.87 if you do it the proper way of doing the sine 56 degrees over the sine 72 degrees on a calculator. Of course, I could also choose something else here. For example, I could do this one here. But then, of course, I have to change this one here as well, and again go down to 56 degrees. They didn't say what each one of these index of refraction is, just what the ratio is. But again, if I do here now 1.38 over 1.57, I should come up with the same 0.87. This problem reads: the drawing shows an optical fiber that consists of a core made of flint glass, which is an index of refraction of 1.667, surrounded by a cladding made of crown glass with an index of refraction of 1.523. A beam of light enters the fiber from air at an angle theta 1 with respect to the normal. What is theta 1 if the light strikes the core cladding interface at the critical angle theta c? And that critical angle here is important in order to cause total internal reflection so that the light ray doesn't get out of the optical fiber. So there is a maximum angle at which the light ray can enter. Anything below that, it will stay in the optical fiber. Anything above that would actually leave it, and of course that would be not wanted in an optical fiber. Okay, let's start over here. This one is relatively straightforward to determine. We just have to look up the formula for the critical angle, which is sine theta c equals n1 over n2. And just to point this out, you find this as well in the book, that this one here, this one, and this one here go with this material here. In this case, that would be the crown glass. Hold on. Oh, I'm sorry. The flint glass is the inner one. There you go. Which makes sense because it has to have the higher index of refraction. And this one here goes with the crown glass. Looks pretty much like Snell's law. In fact, it is, except the crown glass is missing its sign. Well, at the critical angle, the angle with which it would leave the the optical fiber here, the flint glass, would be 90 degrees, so it would be along the surface, and it just doesn't exist. But if you do the calculation, sine of 90 degrees is 1, so that sine here is actually sine of 90 degrees, and we're back to Snell's law. Okay, just a matter of plugging in numbers. So theta c equals the inverse sine of the two indices, and that would come out in degrees. So I'm going to do this one here quickly. Inverse sine. Okay, I just got interrupted a moment ago, and I know where I left off, but I don't think I can complete my sentence here. So in any case, I'm going to type in the inverse sine of, what was it again, 1.667. Oops, the other way around. Small index of refraction divided by large index of refraction. So 1.523 divided by 1.667, and I come up with an angle of 66 degrees. Now this one here would therefore be the 66 degrees. I'm going to put this over here still. And that angle over here would be the complementary angle, so that would be 24 degrees. And then of course, in order to figure out, and this here I would call theta 2. So this one here would be theta 2. And of course, theta 2 equals 90 degrees minus theta c. And I believe you can see that geometry. And then the rest is just use Snell's law on that one. So we would have sine theta 2 equals the index of refraction. Oh, whoops. Hold on. That's not my unknown. Sine theta 1. That's my unknown. Sine theta 1 equals n2, which again would be the flint, times sine theta 2, which is the 24 degrees, and the flint here is the 1.667, divide by the index of refraction of air. Apparently over here it comes from air, so divide by 1, and then of course take the inverse sine, and it comes out to theta 1 equals something in degrees, and I'm going to do the same thing I did before. I won't write it down, but I'll just do it on the calculator. So I have 90 minus 66 degrees, that's 24 degrees, and then I'm going to do the index of refraction, which is 1.667 times the sine of that angle theta 2, divide by 1.00, enter, and take the inverse of this one. The inverse sine of this one, and I come up with 42.67 degrees. This problem reads, reflected and refracted rays are perpendicular to each other when light strikes the surface at the Brewster angle. This is equivalent to saying that the angle of reflection plus the angle of refraction is 90 degrees. Using Snell's law and Brewster's law, prove that the angle of reflection plus the angle of refraction is 90 degrees. So what I have here is that incident light hits a surface between two transparent materials. Part of it is refracted and by that partially polarized. The other part is reflected and by that polarized. So at one particular angle, the Brewster angle, the reflected light is going to be completely polarized. So if you used polarized sunglasses and you're looking at the reflection of something at the exact Brewster angle, you will see that there will be no reflection for you, and you can look directly into the water for whatever reasons, for example going fishing. That's why I use polarized glasses. Okay, so let's do the calculation. Respectively, it's not really calculations, it's a lot of algebra. Here is Brewster's law. So the tangent of the Brewster angle equals N2 over N1. So the ratio of the two index of refraction. And then Snell's law I'm also going to write as N2 over N1, because then I can substitute this here the sine of the angle 1, that's the angle with which the light is incident, which is also the Brewster angle. So theta 1 equals theta b by sine theta 2. So yeah, I'm going to set these two equal. So I'm going to have tangent theta b equals that expression over there. Instead of writing the whole thing, I'm just gonna I have to write the whole thing. I wish I could copy it and paste it, but I think it's just as bad trying to do that. Okay, then I look at that, well, the tangent is the identity of sine theta b over cosine theta b. And really, I wish I could copy this. Oh, I can. There we go. Alright. Because writing on this tablet is just not the easiest thing to do. Get this out of further away here. There we go. Okay, and now I realized that, as I said earlier, the theta 1 is the angle of incidence. Well, that's the same as the Brewster angle because it happens to be the angle of incidence right now. That means the two numerators are exactly the same. Now, they don't come out to 0 because we're dividing by them, so they come out to 1. So the numerators are both divide out and leave a 1 behind, which means only the denominators are left, and so cosine theta b equals sine theta 2. So the Brewster and cosine of the cosine of the Brewster angle equals the sine of the refracted angle. And then on the right hand side I'm going to use another identity, and that is that the sine can be rewritten as the cosine being 90 degrees minus theta 2. Never likes me to write small letters or symbols. And so I have cosine and cosine on the both sides, so I have the Brewster angle equals 90 degrees minus the angle of refraction, and the angle of refraction is this one here, and the Brewster angle is this one here, and so the difference between is 90 degrees. And I know that's what the drawing says, that's what the book said, but this was a proof of that is indeed the case. At when these two angles are at 90 degrees to each other, then the reflection of the surface is completely polarized, and the fisherman can, or woman, can use polarized glasses and get totally rid of the reflection, or the photographer who has to photograph through a window is able to get rid of unwanted reflections on the window.